Okay, so we'll start the morning session. It is my great pleasure to introduce our Australian colleague, Professor Toby Walsh, who is professor at UNSW in Sydney and also has been the acting director of NICTA, which is the Australian main research center in computer science. Toby was the editor of the Handbook of Satisfiability and the editor also of the Handbook of Constraint Programming. And he's really one of the most prominent researchers in artificial intelligence in the world. So we're really great that he's here, and he's been one of the few people pioneering the very many possible applications of parameterized complexity in artificial intelligence, which has lots and lots of input structure and lots of natural parameters. Yeah, I'd also like to mention that Toby has one of the most beautiful web pages that you've ever seen. You ought to have a look at it. And it will inspire you possibly to come to Australia, because it's a serious possibility that in 2012 this meeting may be located in Australia. Thank you, Toby.
Thank you, Mike. I'm very pleased and honored to be here. It was very kind to be invited. So this is going to be a bit of an application talk. I'm an AI person, so I'm interested in applying these things. So I hope it's interesting for you to hear about how people have tried to take some of the ideas being developed in this community and applied it to some practical search problems. I also think it might be interesting, listening to some of the talks over the last couple of days, it's dawned on me that actually many of you really are interested in particular search algorithm, backtracking search algorithms, and so some of the ideas I think actually may be useful even at the object level, in the sense that symmetry occurs in many NP-hard problems, and probably in the NP-hard problem that you're interested in. And we have developed a very good idea or understanding of what symmetry is over the last 10 or 15 years and how to deal with it. And so I hope I can plant some ideas in the back of your mind so that when you do come across symmetry next in a particular combinatorial problem, you'll actually know immediately how to deal with that, and some of the effective techniques that have been developed in AI and elsewhere to deal with symmetry. So I hope that the talk may appeal to you on a number of different levels. I'm very happy to take questions, by the way, during the talk. I may be making AI-like assumptions that surprise you or intrigue you, so please feel free if you want to ask questions as I go along. To make the talk accessible, I know we've got a very powerful theory audience here, but I'm going to keep the group theory out of it. I'm just going to focus on the search side of things and assume a pretty high-level understanding of what groups are. Symmetry is, of course, all about group theory. Symmetries form a group under the usual composition operation. And I would just like to flag that there's this well-developed theory of computational group theory with some beautiful algorithms that many of you will probably know about, things like the Schreier-Sims algorithm. These do get frequently used in practice in the sort of work I'm talking about. I'm not going to go into too much details about these, but just to flag to you that those sorts of ideas and algorithms are also particularly useful here, but I can get away in this talk without going into too much technical detail about that. So it's a what, why, how talk. I'll tell you what is symmetry, and I'll define it in a reasonably formal way. I'll briefly mention why it's a problem when we're looking at solving NP-hard problems. And then most of the talk, more than half the talk, is about a very well-developed body of theory that myself and a number of other people in AI have been working on, how to deal with it. And you'll see we get to use fixed parameter tractability in understanding what we can and can't do in dealing with symmetry. So that's the application side of things. In fact, I've even got some graphs with some computational experiments to report to you, which I think is quite... so we'll have at least 2 papers presented in the conference with computational results. So I hope it's useful both as an application and also, as I said, I think you'll see that the ideas I'm talking about are actually quite general, And you may have a graph theory problem or a problem in some combinatoric problem where there is symmetry as well. And I imagine, I would expect, you could probably take some of these ideas, map them into the language of your problem, and find maybe that they're quite useful for you. So I hope also you may take away something in the more algorithmic sense from this talk. Okay, so we'll leap into the talk. What is symmetry? Now, I hope the slide wasn't wasted on you. Of course, symmetry is a common feature of nature. There's a beautiful six-fold symmetry on that snowflake. Symmetry turns up in a large number of combinatorial problems, in a large number of natural problems. Of course, there's beautiful mathematical objects with lovely symmetries like this. Here's one. This is one I was looking at myself. You can see there's threefold and fivefold, threefold, and fivefold symmetries here. And this is a pictorial representation of a number theoretic problem that I'm going to talk about hopefully if I have time, at the end of the talk. So it's actually some new objects in design theory that we actually found using some AI search algorithms and exploited the symmetry in them to actually make the search problem more tractable. Of course, symmetry is also a very real problem, a very real feature of the sorts of practical decision problems that you might actually meet in industry. In practice, if you are British Airways and you had to schedule flights out of London Heathrow where you've got half a dozen 747s there to schedule, the serial numbers of the airplanes is not particularly relevant to the scheduling problem. And in fact, you can really treat those 747s as indistinguishable from each other. So they're essentially symmetric to each other. If we come up with a schedule for those 747s, we don't want to come up with all the symmetric schedules which just permute the serial numbers of the 747s. That's not really a new schedule. It doesn't, it's just enlarging the search space. Of course, those sorts of symmetries turn up in lots of other domains. If you're FedEx, I spend a lot of time looking at vehicle routing problems. If you're delivering packages like this out and you've got a bunch of delivery lorries, well, all these lorries have got the same carrying capacity and they're parked in the same depot. Again, we're not interested in their number plates. We're just interested in the fact that you've got four delivery trucks to schedule, and we want to factor that symmetry out of our problem. There are many other practical problems here. If you're rostering staff in a call center, well, if these people, if they have all the same skills and the same availability, then we don't want to come up with schedules that just permute these people around. A problem that some colleagues of mine were looking at, scheduling production in Nissan. Here's the production line for building cars. Now, it might be that all the white cars are essentially the same and all the blue cars are essentially the same. If we're coming up with a good schedule, a good order to put the cars on the production line, then we don't want to come up with all the permutations of the cars that are essentially the same spec. And that's a very, very real practical problem. Nissan were the first people in the world to actually build two different types of cars, two models of cars on the same production line. And that saved them tens of millions of dollars and created a large number of jobs in the north of England when they were able to work out how they could actually solve that scheduling problem. Okay, so that's a whistle-stop tour of some examples of problems with symmetry in. I hope I've convinced you that symmetry is an important feature in practical problems, in mathematical problems, and just as an object to understand. So I'm going to now talk about formally what symmetry is. I'll look at graph coloring. I'm sure everyone in the audience knows what graph coloring is. We're assigning colors or values to countries or nodes, vertices, which are the variables in our problem. So here's a proper coloring of a particular graph. Now, there's a nice symmetry in this problem, which is the symmetry of the colors, the values are interchangeable in this problem. If I swap yellow for red throughout this graph, if I had a proper coloring at the start, I've swapped yellow for red, I've got a proper coloring at the end. If I swap back yellow and red, I've got a proper coloring. So I can swap the colors around Here I'm permuting yellow and red, but I can do any permutation of the 4 colors in this graph and I'd be okay. So that's an example of a symmetry. We can formalize it. A formal, this is as mathematical as the slides get, in notation sense at least. It's a bijectional assignment. So here, if we have an assignment that assigns Portugal, the country, to red, and we look at the bijection sigma that maps that onto Portugal, the country, green, and at the same time that bijection maps anything that's green, Spain is green in this case, to Spain to being red. So we can describe symmetry just by thinking of the bijections on the assignments that are happening in our problem. Of course, there are lots of bijections. Many of them are not what you would think of as symmetries. So we focus just on those symmetries, like in the graph coloring example, that map solutions onto solutions. When we interchange colors, if we had a proper coloring, we mapped it onto a proper coloring. So we're interested in the bijections that preserve the notion that we have a solution. This is a name that I'm going to call this type of symmetry. This is called a value symmetry. This is because it's changing the values, the colors. And you'll see that value symmetries turn out to be a particularly tractable case and have particularly nice properties that we'll be exploiting. It's mapping the value red everywhere onto the value green and vice versa. And of course, there are other types of symmetries. We can have symmetries that act simultaneously on the vertices or the variables in this problem. So now I'm going to stretch your geographical knowledge. Those people from Scandinavia will know that Finland and Norway neighbor the same countries as each other and the sea. Right? They both neighbor each other, they both neighbor Russia, and they both neighbor the sea. Right? So as countries, right, if we swap the colors that we assign to those 2 countries just amongst themselves, if we had a proper coloring before, we'd have a proper coloring afterwards. So for example, if we had Finland labeled orange and Norway labeled green, if we swap Finland for Norway, so we now label Norway orange and Finland green, but leave all the other colors in the map the same, then if we had a proper coloring of the map before, we'll have a proper coloring afterwards. So you can see that symmetries there are acting on the vertices or the variables in that problem. And that's what we would call a variable symmetry. So that's all you need to know about what is a symmetry in a formal sense. I'm going to spend the rest of the talk talking about why it's a problem and how we deal with it. The why it's a problem is actually very easy to see. This is a very short part of the talk. Let's go back to our coloring problem. Suppose we have m colors in our problem. They're all interchangeable. Any permutation of those colors would be a solution, right? There are m factorial possible permutations. There are m factorial symmetries of that problem. So that means that if we've got a proper coloring, there are m factorial symmetric solutions to that coloring. And we don't want to find all m factorial symmetric solutions. If you're interested in all those symmetric solutions, I can give you a very efficient algorithm that will enumerate them for you. You give me as input the solution, and I can generate you in a very efficient time all the symmetric counterparts to it. But I don't want to leave those m factorial solutions in my search space. Right? I can factor those out of my search space. So that's one reason. In fact, probably even more important reason, though, is not the symmetric solutions, but it's the failing search states as well. Because for every failing search state, there's m factorial symmetric counterparts to that. If I'm, imagine exploring a backtracking search tree trying to color that graph, if I get to some node in that backtracking search tree and I find out that I can't extend the coloring anymore without using another color, well, any symmetry of that state will also fail. So you can see that the search space has increased by the presence of symmetries dramatically. And it's getting rid of those symmetries of the failing states that, in fact, is perhaps most important from a search perspective in dealing with symmetry. Generating extra solutions, symmetric solutions, is perhaps not as problematic as the fact that the search space is just so much bigger, m factorial bigger than we need it to be. Okay, so having hopefully convinced you that symmetry turns up in a lot of problems and that symmetry is an issue that you have to try and factor out of your search, I'm going to spend the rest of the talk talking about, well, how do we deal with symmetry? And the title of my talk talked about symmetry breaking, and that's what we're going to be talking about. But By symmetry breaking, I mean we add constraints to the problem that remove those symmetric solutions. They will also, as a nice positive side effect, remove symmetric failing states as well. I should point out there are other things you can do. People have looked at modifying the search algorithm itself so it never branches into symmetric states. That's a possibility. There's some interesting techniques that have been developed in that way. There is, however, a strong theoretical reasoning to think about the first, about actually adding constraints to your problem that removes symmetric solutions. In particular, you can give theoretical examples, pathological examples. The canonical one is a pigeonhole problem, on which if you add the symmetry breaking constraints to factor the symmetries out of the problem, you can prove that it's exponentially faster than just not exploring symmetric search states. That you get useful synergies between the symmetry breaking and the problem constraints, and that can actually march you to a solution in a backtrack-free way, whereas you might still, on the same representation, take an exponential amount of time if you just made sure you never visited symmetric states. So there's strong theoretical reasons, and the experience of people in practice in AI is that adding symmetry breaking constraints is really important to solving these problems effectively. Okay, the nice thing is there's a very general method that has been developed to deal with symmetry. It tells you how to get rid of symmetry in the problem. And this is one slide. If you take nothing away from my talk, this is the one slide that I hope you can take away, because this is the idea that if you see symmetry in your problem, you can do the same thing in your problem, and it will solve symmetry or eliminate symmetry for you. And it's called the Lex Leader method, and it's a very simple, very obvious idea, which is if we want to make sure that we get rid of the symmetries of our solutions, we say that we'll take the solution that is lexicographically least, the least solution, in each symmetry class. Now, when we say least solution, we need to have some ordering on solutions, and the normal way that most people have found a quite effective way of defining least is put an ordering on solutions, is to put the lexicographical, it's the very natural ordering, to put on solutions. So we write out our solution. In some ordering, and we say it's lexicographically less than the symmetry of that solution. And if we post those sorts of, if we apply those constraints to our problem, we'll only come up with this solution, and this solution will not be allowed, because that will be lexicographically greater than its symmetry. Right? And that's how you deal with symmetry. That's almost at this point, I could just walk away and say, you know everything you need to do about symmetry. Or you know everything about how to deal with symmetry in general. There's lots of special tricks you can do to exploit properties of the symmetry group. But if you just want the general technique, that's what you need to know about. So I've got a little example. We go back to our map coloring problem. We've got Italy, France, Germany. We've ordered the countries in that order. And we're looking at that same symmetry that interchanges red with blue. Okay? So we write out our solution, Italy, France, Germany, and so on, and we say it's lexicographically less than the symmetry of the solution. So suppose we have a solution where Italy is blue, France, communist red. Then we say that's lexicographically less than the symmetry of that solution. Well, we know what the symmetry of blue is, that's red, and the symmetry of red, that's blue. So we say blue-red is lexicographically less than red-blue. Well, if we're treating these as strings in the usual alphabetical order, this vector of strings is lexicographically less than this vector of strings. Right? And the symmetric solution, where we go red-blue, that's lexicographically bigger. Red is alphabetically after blue. Right? So in the usual lex order, dictionary order, this string is lexicographically bigger than this. So this solution will be ruled out. We allow this solution. So it's a very simple idea, nothing deep and too meaningful about it. That's how you can get rid of symmetry. You just say your solutions are the smallest ones in each symmetry class. Of course, we may have many symmetries in our problem. In the graph coloring problem, I said there are m factorial symmetries. Well, you can write down such constraints for every possible one of the symmetries, sigma 1 upwards. And that's why the talk hasn't finished. The reason being is two things. One is that, well, if you know anything about constraint propagation, decomposing problems into different constraints tends to hinder inference propagation. That's definitely true in this case. There's also a very practical reason, which is there's an exponential number of constraints you may have to write down, and of course that's going to blow up in your face. So the rest of the talk is saying, well, how can we deal, what are the special cases where we can deal with this problem more tractably? And then we'll see some, I promise you, coming up very soon, there are some parameterized complexity results coming up soon, so just hold your breath. So that, in theory, is how we deal with multiple symmetries. In practice, we may have lots of them. Was there a question?
Yeah. How do you detect the symmetry?
Good question. I have so far ignored how you detect symmetries. There's some interesting work on that. Often you can just look at the problem and you know that if it's a graph coloring problem, I know ab initio that there are going to be those symmetries in the problem. But you can turn symmetry detection into a graph isomorphism problem. So there's some, and graph isomorphism, although we don't know its true complexity, graph isomorphism algorithms like Sorcy, Naughty, and Torty tend to actually find symmetries in this graph very quickly. So you can quickly detect symmetries using graph isomorphism if you don't actually know from looking at the problem what the symmetries are going to be in advance. Thank you. In fact, it's not hard to prove that getting rid of all the symmetric solutions, since there's an exponential number of symmetries we may have to get rid of, it turns out, not surprisingly, that this is an NP-hard problem to solve, to find out whether we've actually got rid of all of the symmetries in the problem. There are some very interesting tractable cases. One of them I've already talked about, which is value symmetries. There was a very nice result by Jean-François Puget 5 years ago showing that you could break any number, even an exponential number of value symmetries, with a polynomial number of ordering constraints. Now, I'm going to skip over the details because you'll see an example of this in about 3 slides' time. But just take it on faith for a second that if we've got value symmetries, it turns out that's a very tractable case. Even with an exponential number of symmetries, we can eliminate all the symmetric solutions in polynomial time. Now, in fact, there's a difference we make between eliminating all the symmetric solutions and pruning all the symmetric values. This difference, this is a fundamental difference to understand in this talk, which is the difference, if you're thinking of, say, a backtracking search tree, the difference between eliminating the symmetric leaves of the search tree and eliminating the symmetric internal nodes of the search tree. So I've just said that eliminating the symmetric leaves of a search tree when we have value symmetry is polynomial, but it turns out eliminating all the symmetric internal nodes of the search tree is NP-hard, even if we bound the number of symmetries. It's not the large number of symmetries that get in the way. Even if I only have a linear number of value symmetries, getting rid of all the internal symmetric nodes in the tree, all those failing symmetric states that I talked about, is NP-hard. So you can see that value symmetry is a tractable case, but it's only just tractable. We can get rid of all the symmetric leaves in the search tree, but we can't get rid of all the symmetric internal nodes. So yes, that slide's just, the bottom of the slide is just saying the same thing. We're right on the boundary of tractability, and that's why parameterized complexity looked to me to be a really interesting tool to look more closely at this boundary of tractability. So we have slightly better news. We certainly have evidence that suggests that some of the complexity comes from having many value symmetries. So here's the first fixed parameter tractability result. If we take our parameter as the number of value symmetries, then there's a dynamic programming algorithm that will prune all the symmetric values, that's prune all the symmetric internal nodes of the search tree in polynomial time. So we see that it's the large number of value symmetries that is one of the reasons for getting the complexity. If we can bound the number of value symmetries, then we can actually do it in polynomial time. There's a very special, nice little case that I want to talk about. This illustrates how you can get rid of all value symmetry, even when there's an exponential number of value symmetries. And it's the case, in fact, that we've already looked at in graph coloring and also in the scheduling of those 747s and of the vans, It's a really common case that we see in practice in logistics problems. It's where the values are interchangeable. Any one of the permutations of the values is a solution. And there's a very nice idea. It's a technique that's been rediscovered in many areas. I've seen it being used in bin packing. I've seen it used in satisfiability. I've seen it in constraint satisfaction and graph coloring. And I'm sure almost any other problem, people have used essentially this technique. They've renamed it the least number heuristic. They've renamed it many other things. But I'm calling it under the name today of value precedence. So if we think of our values as numbers, we're going to say that the values occur in order. In particular, that means the first occurrence of 1 occurs before the first occurrence of 2. The first occurrence of 2 occurs before the first occurrence of 3. The first occurrence of 3 before the first occurrence of 4. So here's a solution we've written out: 1, 1, 2, 1, 3, 2, 4. And we see 1 occurs before 2, 2 occurs before 3, and 3 occurs before 4. So that's a string that satisfies this value precedence property. And you see, it's not hard to see, there's a very nice DFA that will actually recognize strings in that language. And in fact, that's the basis for a very nice inference algorithm, a propagator, for reasoning about such strings. And here's a string where I've permuted 3 and 4. 4 now is here and 3 is here. And you see that this string does not satisfy value precedence. 4 now occurs before 3. If we insist that the strings satisfy value precedence, we cannot permute the numbers around. If we reorder the numbers, then we will break the ordering that the first occurrence of I is before the first occurrence of j for I less than j. So insisting this constraint eliminates an exponential number of symmetries of the problem. One of the reasons I want to talk about that case is that this is a nice example of where, in fact, what we're doing is actually breaking the generator symmetries. The generators of a group, if I remind you, are those elements that generate the whole group. We can think here of the one set of generators is the set of neighborhood swaps. We swap 1 with 2, 2 with 3, 3 with 4. So with those neighborhood swaps, we can generate the whole group of permutations, right? This, essentially with this symmetry breaking, we're preventing those neighborhood swaps, and actually that breaks all symmetry. So in this case, we have a parameter that describes the symmetry in our problem. It's the number of generators. The number of generators is really interesting, really nice parameter to have to be focusing on, because there's a very nice result which says that the number of generators in the problem is at most a log of the number of symmetries in your problem. Right? So you can have a very small number of generators generate a very large symmetry group. And that's the case here. We have a linear number of generators, the neighborhood swaps, that generate any one of the m factorial. So there are m neighborhood swaps that generate m factorial possible symmetries. And because now we've reduced it to just focusing on the generator symmetries, and I said to you, if we only have a small number of, if the parameter is the number of symmetries, we get tractability. So we're getting tractability here because the parameter is the number of generators. Breaking the generators is enough to eliminate all the symmetry in our problem, and there's only a small number of generators. So it's a really nice parameter to focus on. Unfortunately, it's not all good news. I've got some examples coming up later on in the talk where I can show to you breaking the generators is not enough to eliminate all the symmetry in the problem. It tends to be a very effective method, but as you'll see, it will actually leave some symmetry in the problem. So sometimes focusing on the generators is not enough. But in this case, it is enough. And it's really, if you want an interesting research problem, it's interesting to know what are the useful symmetry groups where it's adequate to focus on just the generators. That's a problem where we know this one case. We have a few positive examples, a few negative examples, but we have no general theory to understand when is it enough just to focus on the generators. It would be a really interesting result to know under what characteristics to say that the generators are enough. Just to show you that we're really on that boundary of tractability here. We looked at the case where the values are all interchangeable amongst each other. We can look at a slightly more general case that also turns up a lot in practice, which is where the values partition into equivalence classes. And within each equivalence class, they're interchangeable, but the equivalence classes themselves are not interchangeable amongst each other. So before we had all the values in one equivalence class, now we're partitioning into k equivalence classes. We now lose tractability. The pruning now is NP-hard. In this case, focusing on the generators for this new symmetry group, the cross product of these permutation symmetries eliminates all the symmetric solutions, so we get rid of all the leaves of our symmetric search tree, but it doesn't eliminate all the symmetric nodes in the search tree. So you see, we're always on that boundary of tractability. We're pushing things backwards and forwards across that boundary of tractability. So if we treat, but the nice thing is if we treat the number of interchangeable classes as the parameter in our problem, the problem now is fixed parameter tractability, and there's a nice dynamic programming algorithm that will break all the symmetry for you. So again, we can understand where that intractability is coming from by focusing on the right parameter, here the number of equivalence classes. I want to spend the penultimate part of the talk now talking about another interesting tractable case. That was value symmetries, in particular interchangeable values. I want to talk about another tractable case. This is a variable symmetry case. It's one that we've seen in lots of practical problems in industry. It again illustrates some interesting ideas about what is tractable and what is intractable. And there's some nice fixed parameter results in here as well. This case is called row and column symmetry. It's a very common class of problems where we imagine we have some matrix of decision variables, and within that matrix, the rows and columns are interchangeable. Many such examples. I've got lots of examples coming up just to illustrate this. Here's an example. Suppose you were scheduling the next World Cup. Here's a simple schedule. We've got 3 weeks and 2 stadium. So, in week 1, in stadium 1, we've got 4 teams. Team 1 plays versus team 4. Team 2 plays team 3 in stadium 2. In week 2, team 1 plays team 3, and then in the final week they play the final team they haven't played against 2. Now, this problem has lots of nice symmetries. If there's nothing special about the weeks, I can commute the columns, right? If I can take all the matches in week 1 and play them in week 2, and play all the week 2 matches in week 1. So any permutation of the columns would be a solution. Also, maybe there's nothing special about the stadium. If I swap stadium 1, all the matches played in stadium 1, with all the matches played in stadium 2, swap these all around, I'd still have a good schedule. Notice this is a round-robin tournament, right? Everyone plays everyone else. And there's a third symmetry in the problem as well, which is that the names of the teams are not important, right? If I renamed team 1 team 3, and if I renamed team 4 team 2, and took some permutation of the names, I'd have another solution again. So that would be a value symmetry. So you can see this problem is full of symmetries. But there are many other problems. Suppose this is a product configuration. Suppose I'm designing some electrical equipment. I've got a bunch of different components that go in different racks, right? I'm making 0, 1 decisions. Component 2 goes in rack 1. Component 1 goes in rack 2. We see that component 2 and 3 always occur together. So they're essentially interchangeable, so I could swap those rows. Oh, look, I'm not going to change the number, the zeros. Whoops, sorry. I'm not going to change the zeros and ones. I'm just going to change the titles, right? So in this case, I changed the racks for depots. I changed the components for trucks. Now I've got a truck assignment problem. I'm working out which trucks could get assigned to which depot to solve my vehicle routing problem. And again, if truck 2 and 3 are of similar capacity, they're in the same depot, we can permute the trucks around. We don't want to come up with solutions where we permute those. Now, the Drosophila example that people look at when they're looking at how to deal with row and column symmetry is this lovely problem in combinatorial design. It's called balancing complete block designs. Many of you will probably have seen these with BIBDs. This is to come up with 0, 1 matrices. These get used for designing statistically independent experiments. You've got a 0, 1 matrix. This is parameterized by this sequence of numbers, 7 by 7. There are 3 1s in each row, 3 1s in each column, and the dot product scalar product between any 2 pairs of rows So between these two pairs of rows is 1. Between this row and this row is 1. So the scalar product is 1. And I give you some parameters for a balanced incomplete block design with particular characteristics that you want, and you've got to go away and find it. Now, in the specification of the problem, there's nothing special about the rows and columns. If I permute the rows, if I had a solution before, I've preserved the row sums, the column sums, and the scalar products, I've got a solution. If I permute the columns, I preserve the row sums, the column sums, and the scalar products between rows. So any permutation of the rows, any permutation of the columns is a solution. Now, if this is an m by n matrix, there are n factorial permutations of the rows, there are n factorial permutations of the columns, there are n factorial times m factorial symmetries of the problem, which of course is a very large number we want to factor out of the search space. So there's a very nice simple idea, which is based upon the Lex-Leader method, to get rid of that large number of symmetries, or many of those symmetries. And that's to Lex order the columns and Lex order the rows. Now, here's a matrix, a 0, 1 matrix, and I'm going to do that on this matrix. So suppose I Lex order the rows. So the smallest lexicographically row is this one, so I put that first. The second smallest is this guy, so I put him second. The third smallest is this guy, so I put him third. And this is the largest, so he goes last. So I've Lex ordered the rows. Now, this was a carefully chosen example, because now if I look closely, if I read off the columns now happen by chance to be lexicographically ordered. So this column is now lexicographically ordered. So this is 0, 0, 0 as a column, 0, 1, 1, 0, and so on. So you see the columns now lexicographically ordered. Now, it's not hard to show that there's always, I can always lexicographically order the rows and columns simultaneously, as long as I have them lexicographically increasing in the same way. I could have done the other thing, which is lexicographically order the columns of this guy. If I do that, this is this lexicographically smallest column, so he goes first. Second is this guy here, the penultimate column, so he goes second, and so on. And now this was a very carefully chosen example because it now happens that these rows now are lexicographically ordered. Right, so again, we've lexicographically ordered the rows and columns, and we've found a canonical element with the rows and columns lexicographically ordered. But I point your attention to the bottom right corner. The bottom right corner here is 1. The bottom right corner here is 0. So these three solutions are all in the same symmetry class. They're all row and column permutations of each other. These two have lexicographically ordered rows and columns. This one doesn't. These two, though, have lexicographically ordered rows and columns. So lexicographically ordering the rows and columns leaves more than one solution in each symmetry class. It leaves at least these two guys, right? So this breaks some of the symmetry in the problem, but it doesn't break all of the symmetry. And you'll see that actually breaking all of the symmetry is an NP-hard problem. That's why we're not, in general, breaking all of the symmetry. So this is what we call a sound and complete method. Sadly, you can illustrate a pathological example, a very pathological example, where it in fact leaves an exponential number of, super exponential number of symmetric solutions. Though breaking all symmetry is NP-hard, we call lexicographically, by the way, we call lexicographically ordering the rows and the columns double Lex, so Lex in both directions, double Lex. We see that we're really on the boundary of tractability because not only is pruning all the symmetric leaves NP-hard, even if we just break some of the symmetries that we do with double Lex, getting complete inference, pruning all the symmetric internal states is NP-hard itself. So we're really on the boundary of tractability here. And of course, we can just break this down into individual ordering constraints on the rows and columns. This is an example, again, what we're doing here, I didn't say it when I first described it, but I will now. We're actually breaking all the generator symmetries. The generators here are the generators that swap neighboring rows and columns. Lexicographically ordering the rows and columns stops us ordering the rows and columns, neighboring rows and columns. And so this is a case where breaking all the generator symmetries leaves some symmetries. We had two matrices, row and column symmetric matrices, that were double lexicographically ordered. So here, we can focus on breaking the generators, but it doesn't break all of the symmetries. It's an effective method, nevertheless, in practice. In fact, after 10 or 15 years looking at these row and column symmetric matrices, this is the best method that we have to deal with row and column symmetries. And here's another fixed parameter tractability result, though. If we can bound the number of rows or number of columns in a problem, so we may have an unbounded number of rows but a bounded number of columns, then we get a polynomial time method to break all symmetry. Now, actually, it turns out in practice there are real problems where you actually do have a bound on the number of rows or the number of columns. A classic example is when you're trying to find error-correcting codes. Suppose you want to find a 32-bit, want a collection of 32-bit error-correcting codes. They're only 32 bits wide. And we may want a large number of them, so the number of columns, so the number of columns is fixed, 32 bits, but the number of rows may be the number of words that we want in our code. So we may have a large number of rows, but the columns is fixed by the word size that we're looking for. So there are lots of practical examples like that where we can actually bound the number of rows or the number of columns. Now this is an example. I promised you that there was some computational results. So actually this is an example where we implemented this algorithm that's essentially behind this. Sadly, it's not a very exciting algorithm from an algorithmic perspective because it's really, as this hint here says, it's really a brute force algorithm. It's looking at all the permutations, essentially, of the bounded number of rows or the bounded number of columns. But nevertheless, it turns out that that's a way for us to actually get rid of all the symmetry in the problem. And so that actually gave us a practical way to really study how complete, or incomplete rather, posting lexicographically ordering constraints on the rows and columns, double X, is. We can actually compute the number of solutions left when we post that sort of symmetry breaking. And because we know we have this fixed parameter tractable algorithm, we can actually construct the number of symmetry-free solutions and compare the ratio of these two. We did this on a bunch of different problems. We looked at both purely unconstrained matrices, so all n by n 0, 1 matrices, or all n by n 0, 1, 2 matrices. But we also looked at some practical ones, BIBDs that I mentioned, error correcting, frequency permutation arrays, covering arrays. There's a whole bunch of combinatorial problems that we looked at. And here's the sorts of graphs that we saw. So this is the size of the problem. So this is 3 by 3, 4 by 4, 5 by 5, 6 by 6. Here's the number of solutions left when we post double X. That's an incomplete symmetry breaking method. Here are the number of symmetry-free solutions. So you see that it doesn't break all symmetries. There is a gap between these two lines. But it's not bad. It's growing quite well compared to the ratio is not the ratio is not getting much bigger as we expand the size of the problem. And you can see, therefore, it's not surprising why double X is a pretty effective method. It's scaling pretty much the same as the symmetry-free method. I just want to end the last 10 minutes by talking about other types of symmetry, just so you get a little flavor of that there's quite a lot of interesting ongoing research areas in this problem, and also because there's some nice open problems in graph theory that we've actually been able to solve by exploiting the symmetries that exist in them. So I thought this audience will be interested in graph theory problems. Every talk seems to have some graph theory here, I reckon. So I thought I'd better put some graph theory in myself. So far, we've been thinking about solution symmetries, symmetries that map one solution onto another. I'm now going to be talking about symmetries within a solution. These have been nicknamed internal symmetries. They mapped, this is very recent work that I presented earlier this year, symmetries that map one solution onto itself, not onto another solution, but onto itself. Now I've got a musical example. Let's see if we can get this to work. Right, here we go. I'm not very musical, but we have a musical example. Can you hear that? Is that audible? Where's the word? Is there? So I'm sure we have musical people in the audience who will. I've always wanted to check that those notes are right. I've had to take it on confidence and faith because I don't read music, and I don't. Even if I did read music, I don't actually have any tonal recognition, so it wouldn't make any sense to me whether. I'm told, at any rate, that that is an all-interval series. It's a sequence of notes such that if we look at the pairwise differences between the notes, every interval is present. So it's an interesting object from a combinatorial perspective. It's one of these things that modern composers are interested in. It doesn't mean it's music then, but at any rate. For those who aren't musical in the audience like myself, you can think of this as a simple mathematical problem. This is the way I think about it. It's a sequence of integers. So here we've got the sequence of integers 0 to 10. So it's a permutation of 0 to 10, such that every pairwise difference, so here we've taken the pairwise difference between 3 and 7 is 4, 7 and 4 is 3, such that every pairwise difference is present. So every number between, this is a permutation of 1 to 10 now. Right? So that's an all-interval series, and you can ask me for musical composers are interested in coming up with all the different possible sequences of notes or integers that has this property, and then they throw them together and make music in the broadest sense of the word with them. So here's that example. There are, of course, many other examples. Here's another example that shows an interesting symmetry. So it's 0, 10, 1, 9, 2, 8, 3, 7, 4, 6, 5. I'm sure you can see how I've generated this. The pairwise differences are the descending sequence 10 to 1. Right? But this illustrates the concept that I wanted to, very simply and very elegantly, the concept I wanted to come up with here, which is the idea of an internal symmetry. This is a symmetry that maps part of a problem onto itself. So if we take 0 and we increment it and map it two further down the sequence, and increment it and then map it 2 down the sequence, and increment it and move it 2 down the sequence, and increment it, move it 2 down the sequence, and increment it and move it 2 down the sequence, we generate all the odd numbers, all the odd positions, all the numbers between 0 and 5. We take the second number 10, decrement it and move it 2, decrement it and move it 2, decrement it and move it 2, decrement it and move it 2. We generate all the numbers between 10 and, oops. For some reason the power's not working. You have to turn them. Okay, power's back on. So we can define. That's all right. We can describe that in terms of a symmetry that maps this assignment onto this one, where we move 2 down in increment, and we take the odd numbers and we move 2 down and we decrement. Sorry, that's not a very good slide. That's -1 there, very carefully hidden away. So that's an example. I just was using that simple example to illustrate the concept. We've applied it to actually come up with some new combinatorial objects and solve some open problems in the area of graceful graphs. Many of you probably have seen what a graceful graph are. Here are some graceful graphs. A graceful graph, it's a vertex labeling. So we see we've labeled the vertices here with numbers. We then label the edges with the absolute difference between the two endpoints. So this would be labeled with 9, 16, minus 7. And a graph is called graceful if all the edge labels are distinct. And there are nice practical applications for finding graceful graphs in areas like radio astronomy and crystallography. We're looking at interference here, right? So if you can find new graceful graphs, these people are really interested in seeing them. Now, one of the games that mathematicians play is they pick a class of graphs and they make conjectures that, for example, all members of this class are graceful. So one of these conjectures that exists and still open is that all double-wheeled graphs are graceful. Here's a double-wheeled graph. So it's a bicycle wheel here with spokes, you see, to a central hub. But it's 2 of them connected to the same hub. Right? So we've got 2 wheels. Here's the inner wheel and the outer wheel. We've got spokes to a central hub, 0, that they're shared. Now, when we started this work, this was the largest known graceful graph. It's two wheels of size 10 with a hub in between, so 21 vertices in total. This was the largest known beast, but mathematicians had seen all smaller examples of double-wheel graceful graphs were gracefully labeled, so they conjectured that all of them were. Now, this problem has lots of, if you want to go away and solve this problem in a constraint solver or something, solve this, turn it into a problem of finding graceful graphs, double-wheel graceful graphs, there's lots of nice symmetries in here. Of course, there's nothing special about the inner and the outer wheel. I can swap the inner wheel with the outer wheel. I've got a graceful graph, so there's a symmetry there, solution symmetry. I can take the wheels and rotate them. Any rotation of the wheels would preserve the gracefulness of the graph. I can also, this wheel reads 1, 3, 7, 12, 18. If I ran it backwards, so it read 1, 3, 7, 12 in this direction, it would still be a graceful graph. So I can reverse the order, invert the order within the graph. And then there's a nice value symmetry, which is I can invert the values. If I take the number 40 and map it onto 0, number 0, map it onto 40. Did I say 40? I've lost where I was. When I map the number 1 onto 39 and 39 onto 1, I preserve the absolute differences. Right? That operation of inverting the values will preserve the absolute differences. So there's a lot of interesting solution symmetries. The Lex Leader method that I told you about will get rid of all those symmetries for you. So we know how to deal with those solution symmetries. But what made a big difference was also looking at internal symmetries in this problem. Now, you might notice this is a much bigger graph, right? In fact, it's got more than twice the number of vertices in it than the last one. So this was one of the new graphs that we were able to show was graceful. And what we exploited was an internal symmetry. If we look here, if we look at the small numbers, so we start here, we've got 1, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, and then unfortunately the symmetry only works on the small numbers and it breaks. And similarly, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and then the symmetry breaks on the larger numbers. So you see for the small numbers, for the bottom half of the numbers in the labeling, we've got this nice move two along and add two that describe the symmetry, the internal symmetry within the problem. And so we actually posted that as a constraint. We found the symmetry on small instances of double-wheel graphs and then posted that as a constraint. So that was an example where we were able to more than double the size. These are very combinatorially difficult to solve. So what you have to do here is you have to find those internal symmetries. That's an interesting challenge because many small instances may have lots of irrelevant internal symmetries. And then you just post, then you just post constraints that your solution has this internal symmetry. This is a very nice constraint. It looks, remember the constraint we posted to break symmetries? We said that this solution was lexicographically less than or equal to the symmetry of the solution. Well, for internal symmetries, we say not the less than or equal to, we just say it's equal to. It maps the solution onto itself. And that allowed us to more than double the size of the largest known double graceful graph. We also found some interesting, if you remember, I said there was a nice picture in the start of my talk with 3- and 5-fold symmetry in the problem. That was a very nice example of a problem in van der Waals numbers, closely related to Ramsey theory, where we were able to come up with some new open instances by exploiting these sorts of symmetries. So the challenge is how to identify useful internal symmetries and ignore the many unhelpful ones. Okay. I just want to wrap up with a few conclusions. I hope I've convinced you that symmetry is an interesting idea. It occurs in a number of different forms. So you've seen two types there, solution symmetry and internal symmetry. One of the things I really do hope might be useful if you take anything useful at all out of this talk is that if you have symmetry in your NP-hard problem, that you should think about it in terms of posting constraints or equivalently doing things that leave just the lexicographically smallest solution in each symmetry class. There's a very general method we have. The problem is if you have a large number of symmetries, then you want to start looking at what properties that your symmetry group have that you can exploit, because the problem is NP-hard. We have looked at a number of useful tractable cases. Interchangeable values is a useful case. Row and column symmetry is a very useful case. And it's turned out to understand there's a we are really very much on the boundary of tractability when we're looking at these problems. You've seen lots of examples where I said, well, it's tractable here, but if we generalize it just a little bit here, it's intractable. We've explored very closely that boundary of tractability. Parameterized complexity has, I found myself, to be a nice, useful tool to get an understanding of what's going on. The sorts of parameters we've looked at are, for example, the number of symmetries, the number of rows, the number of columns in our matrix. One really interesting thing that I mentioned about, and that's still largely not understood, is the number of generators is a very interesting parameter that we have found useful in a number of cases like interchangeable values. It's a really nice parameter. We know it's going to be small, and we know some cases occur where it's enough to break all symmetry. Other cases it's not enough, but it does a good job. So we've got some nice parameters. I think the number of generators is a particularly nice example. But there's, of course, there's many other parameters we could look at to get an even better multi-dimensional view of the tractability, intractability space here. I want to abuse my position by ending with a brief advert to say, please come to Barcelona next July. I am program chair of IJCAI. It's a big conference. We expect to have 1,000 odd people along. We had some very nice fixed parameter tractability, parameterized complexity papers last year. I was mentioning one to Mike in the car this morning. A very nice paper where someone was looking at a meeting, a distributed meeting assignment problem. The problem was NP-hard. They found a nice parameter that would actually give them a fixed parameter tractable algorithm. And they went and then looked at people's schedules and showed in practice that parameter was typically very small. And so that this was actually an effective way. So really nice meeting of theory and practice. So if you have work like that, I'd love to see it being presented at IJCAI. We've got a month or two yet before the paper submission deadline. And just finally to end, actually what I've talked about today is a summary of work that I've done over the last 10 or more years. And it's involved, I haven't given them all credit in line, but it's involved a large number of people in many different countries around the world. I've only been in Australia for five or six of those 10 years, so it's also involved a bunch of my previous funding agencies, so I'd like to acknowledge all of them for their fine support. And just to say, thank you very much. Any questions?
Mm-hmm.
I wondered if you could explain that one more. Isn't there sort of a classic theorem that says that logarithm, any subgroup of a symmetric group on n ladders has a logarithmic number of generators? Is that?
Yes, that's true. So we know. So we actually, I mean, we have examples where we know there are none of the. There's not a unique set of generators typically. There's a unique irredundant generator, but there may be multiple generators of the same group. But we have examples where we know that none of the irredundant sets of generators is enough to break all the symmetry in the group. And of course, we have every expectation, since we know that breaking all symmetry is NP-hard, and we know that there's only a logarithmic number of generators at most, we know that in SP equals NP, we're not going to find, there are going to be cases where breaking all the generators could not be enough. So it's not surprising. But what we don't know is, can we characterize when breaking the generators is enough? We have some common examples that turn up in practice, like interchangeable values, where it's enough. But we don't know why we're lucky in that case, and why looking at another set of generators, if there's some algebraic property that we could look at and compute easily, that would tell us, yes, that's going to be enough in this case or not.
So you could potentially have the parameter be the size of the centralizer.
Yes, something like this, or something, you know. I'm sure, you know, group theory people could really, you know, have a field day here thinking about these problems, which are much more computational, probably, than the sorts of problems that I guess most group theorists spend most of the time focusing on here. And in particular, we focus much of our work on particular symmetry groups like row and column symmetries and interchangeable values, which we know turn up in our practical logistics problems. So there's symmetry, these symmetry groups are ones that I don't think group theorists have thought of being particularly interesting, because perhaps from a group theory perspective, they're not particularly interesting. But from a computational perspective, we know they're very interesting because they turn up, and so if we can have specialized techniques to deal with these specialized groups, it would be fantastic. So there's a lot of opportunity for people to come in here and actually look at these things with fresh eyes, I think.
Thanks. I want to talk to you about that some more.
So, like in branch and reduce algorithms, there are lots of symmetries. You know, when you do this branch and reduce, like for NP-hard problems, has there been some work done to use this symmetry to improve with some algorithm theoretically?
That's again, I think that's something that, as if I can plant a seed of a research idea in people's minds, that's a fantastic research problem. I can't think of any results, like worst case theory results, where people have shown, you know, the results I'm talking about here, we find them usefully practically. And if you want to deal with some of these problems, like these logistic problems, if you don't factor the symmetries out of the problem, you are never solving them, right? Because these m factorials, you know, come up and bite you in the face. But the theory has lagged behind. So so it's a fantastic area if you want to go away and say, okay, let's use the symmetries to come up with some, you know, some better bounds here. That would be hard.
Okay, okay, maybe then.
So in the special case, for example, of interchangeable values, it's polynomial.
Yep. But for you also talked about detecting these things in the inner nodes, didn't you?
So detecting asymmetry is graph isomorphism.
I see. So it's okay. So my question was more or less whether it makes sense to say, well, what about parameterizing with the distance from the leaves? This kind of thing. So in order to see
because
how close you are.
Yeah.
I mean,
so you're right. We have this tractability boundary, which is we have certain special types of symmetry like interchangeable values where we know we can remove all the symmetries at the leaves and we can't remove all the symmetries inside the tree.
Yeah.
No one's explored. You know, okay, so there's a boundary shift at some point, right? So at some point the problem changes from being tractable, right? So presumably we can parameterize into the depth of the tree. Again, it's a fascinating research problem if someone wants a problem to go away. So how much, you know, how far into the tree can we go? Because we know we can go, the leaves is polynomial, we know the whole tree is NP-hard, so where does the intractability bite?
I mean, that might be even something within the line of thinking of Sackett as well, because you might balance this out, this kind of FBT thing, if it is FBT, with this usual search tree stuff, which you usually, you might then finally detect the symmetries and stop your computation, thing like that. Anyway, so.
Anyone else have a question? Okay, well then let's thank Toby again. Potter, who recently finished her PhD as the first PhD student of Daniel Marks and has gotten one of the finer prizes in computer science, namely a permanent job at Eötvös Loránd University and also at the Technical University in Budapest. Ildi's going to talk about computing the deficiency of housing markets with duplicate houses. While they're getting the computer going, I'll just make a miscellaneous announcement. Francis and I are organizing a workshop on parameterized complexity in Darwin in July or August, and I was very pleased with in July. Do you know the dates, Fran? 11, 12, and 13. And The title of the workshop is not a parameterized complexity, not about graphs. So I was very pleased with Toby's talk pointing at new and useful horizons in that direction. We'll have a website and more information in the near future, in the next week, say.
Anybody would like to? Okay. Also, I'm the editor of the Parameterized Complexity newsletter and moderator of the wiki. The wiki is at... Okay. So if anybody would like to receive the newsletter who's not receiving it, please let me know, and I will put you on the mailing list. Thank you.
Ildi?
My name is Ildi Schlotter, and I'm going to work about housing markets and a special case of housing markets where there are duplicate houses. And the work I'm going to present is joint work with Katarina Cehlarova from... Is it okay? Can you hear me? Good. So this is joint work with Katarina Cehlarova from Safarik University in Košice, which is in Slovakia. Okay, so what is a housing market? The housing market is a very fundamental concept in economy. It was introduced by Shapley and Scarf, and so the model is very simple. There are people and there are houses, and every person owns exactly one house, and of course people have preferences over houses, over each other's houses, and where they want to trade. And these tradings are described by this housing market, and people have looked at it like since this model was introduced. Okay, so what is the motivation? There is also a theoretical motivation behind this model because it's basically the simplest model where we have indivisible goods. So this is interesting for economists from a theoretical point of view, but there are also quite surprising practical applications like really real-world housing markets. For example, there are large-scale exchange programs for housing problems in China, and also housing market model was used in campus housing. And there are even some miscellaneous applications like kidney transplantation. Okay, so one of the most important concepts connected to housing markets is the concept of economical equilibrium. And what is an economical equilibrium? It somehow describes a stable state of a market. So what is this? First, we have a price function, which is just a price for each of the houses, and we also have a balanced allocation of houses to people, which describes the trading. And what does this mean, a balanced allocation? So first of all, everybody buys for the same price as he sells. So this somehow describes that no real money is involved. And the second thing is that everybody gets a most preferred house within his budget set. So we don't want a situation, we want to avoid a situation where somebody could buy a house that he prefers more than the house that we allocated to him. Okay, and what is the budget set? The budget set of a person is basically the price of his house. Okay. Okay, and it's known that an economical equilibrium always exists and can be found in polynomial time by a nice and simple algorithm called top trading cycles, which was invented by Gail Shapley, and Gail. And okay, so here is an example. So we have three persons, A, B, C, and D. A, B, C, D, and E, sorry. And here are the houses. These lists are preference lists. So this means that this is the favorite house of A, which one looks like a face, and he prefers So his second choice is this greenhouse, and the third house is his own house. So we don't represent in this preference list the houses that he thinks are worse than his own house, because he would of course never move into such houses. Okay, so this is just the housing market, and we can see that there is an economical equilibrium for this market. If we set prices like this, and there will be two trading cycles, like A and D trade and B and C. So if you look at the picture, you can observe that for A and D, so this is A's house and this is D's house, and A prefers the most D's house, and A's house is the best choice for D. So of course they want to switch, and they switch. And the price is the higher price in the market for these houses. Okay, and then you can have a look at E. So what's the situation with E? After A and D switched, they will not give their houses to E. Okay, so E stays and doesn't trade at all. And B and C, if you eliminate all the houses that already have an owner in our new allocation, that you can see that these houses remain, so they also want to switch. Okay, so this is indeed an economical equilibrium, as everybody gets the most preferred house in his budget set. Okay, is the example clear? Okay, if not, then please tell me, because we are in the beginning. Okay, so we studied an extension of this model where we can have duplicate houses. So what are duplicate houses? They are basically identical houses. So houses that look the same, and they are basically the same. And the most important thing is that the price function, so the price of two identical houses or two duplicate houses must be the same. So we don't have a price function for each, assigning a real number for each house anymore, but we have a price function for house types, for each type of the houses. And I have to, so I want to mention that duplicate houses doesn't mean that we have two of the same type, but we can have arbitrarily many. So the multiplicity can be more than two. Okay, and what is known about this situation, this model? So an economical equilibrium does not always exist, but if the preferences are strict, then we have a polynomial time algorithm for deciding if such an equilibrium exists. But in the case when ties are possible, then it's NP hard to decide if such an economical equilibrium exists. Okay, so there is some kind of intractability in this model. Okay, here is an example. The same, like we have 5 people, but now A and B have the same kind of houses. Okay, so this brown house is the same. Okay, and here you can see that there is no economical equilibrium. So look at the preference list, and you should say that both A and B prefer this face-looking house the most. Okay, but of course they cannot get one because there's just one of these houses, and it's owned by D. And what does D want? D wants this brown house, which could be either E's house or B's house. But as neither A, neither B can get D's house, because, okay, so one of them could get, but if we set a price where they can buy, so if we said that the price of this house is the same as the price of this house, which means that they could trade, then this would mean that also A would be able to buy this and B would be able to buy this. So if this allocation would result in an economical equilibrium, then this would mean that both of them should have the most preferred house in their budget set, which is this house, which is not possible because there is only one of this kind of house. Okay, so this means, what does this mean? This means that this house should be more expensive than the house of A and B. And then they can be still happy, theoretically, because if this house is not in their budget set, that they are not, then they are somehow not sad that they can't buy it. Okay. But if this is pricier than the brown house, then D must be, in this sense, unsatisfied. Okay, because D has a more expensive house than this brown one, and more expensive means that the price is strictly bigger, which means that they cannot trade because the allocation is balanced. And for this case, D cannot get this house even if it's the most preferred house in his budget set. Okay, so are we okay? Do you understand this example? Okay, good. Okay, so since so it can happen that there is no economical equilibrium, we relaxed the notion of equilibrium and we defined alpha deficient equilibriums where there are only alpha, so a limited number of agents who are unsatisfied in this sense. So there can be at most alpha agents who do not get the most preferred house in their budget set. Okay, and of course we aim for the smallest alpha as possible, and we keep this assumption that we are looking for a balanced allocation, which means that everybody sells at the same price as he buys a house. Okay, and we define the deficiency of the market as the minimum alpha such that there is an alpha deficient equilibrium for the market. And of course, if the deficiency is 0, that means that there is an economical equilibrium for the market. Okay, and so this is just the previous example, and I won't go through it again. But it's easy to construct an alpha deficient equilibrium like this. So here are the prices. You don't really have to go through it, but you can believe it to me that in such an allocation, only D will be unsatisfied. Okay, so the owner of this house will be unsatisfied because he won't get the most preferred house in his budget set. Okay, so what was known about this problem? Basically, all the previous results were for the case of deficiency 0. And as I have told you, there was a polynomial time algorithm solving or deciding whether there is an economical equilibrium. But on the other hand, the problem is NP hard even under a special case of preferences so the model is so-called trichotomous, so everybody has 3 groups of houses: the houses that are better than his own house, the houses that are equivalent to his own house, and houses that are worse than his own house. Okay, so what about the general problem? We proved NP hardness in the case where the preferences are strict, and even if the preference lists are short, in the sense that every person has just one house that he prefers more than his own house. Okay, so of course, that's why we looked at parameterized complexity study, and there are quite a lot of possible parameters here, like you can take alpha as a parameter, you can take the number of different house types as a parameter, you can take the maximum multiplicity of a house type as a parameter, or the number of house types that an agent prefers to his own house. Okay, so I already told you a couple of examples where the problem is not even in XP unless P equals NP. So it's NP hard even in the case where we want to decide whether there is an economical equilibrium, and it's NP hard even in the case where there is only one house that an agent might prefer to his own house, and each of the house multiplicities, house type multiplicities is 2. Okay, so what are our results? This is the NP hardness result I just told you. We have a W1 hardness result with parameter alpha for a case where the preferences are strict and everybody prefers at most 2 houses to his own. But luckily we have some positive results, an FPT algorithm for the case where the parameter is the number of house types, and also a polynomial time algorithm for the case where alpha is constant and the preferences are strict. So alpha is the deficiency we are looking for. Okay, so how much time do I have? Like 8 minutes, okay. So then I think I will only talk about the positive results. I guess you are happy about this. Okay, so first of all, we have this algorithm for the case where the parameter is the number of house types. So what can we do in this case? First of all, we have to guess, or we can guess the prices of the houses. Of course, the exact values don't really matter. The only thing that matters is somehow the order of the prices for each of the houses. So we can just say that each price is an integer between 1 and the number of house types, and we guess the prices. And then what do? Well, we only have to think a little bit about the problem, and I guess everybody would come up with the same algorithm here. So we collect those houses that are somehow the best possible houses, or the best types of houses for an agent A, which is those house types that A prefers the most within his budget set. So we already know what's his budget set, and that helps a lot. And then we can say that some of the agents are surely satisfied in the sense that they get the most, or a most preferred house in their budget set. And this happens if his own house is one of the best possible choice for an agent. And of course we can find agents who are surely unsatisfied, and this happens if the best possible choices are houses that have, so if all of them have a lower price than the house of than the original house of the agent A. Okay, so of course it's a little bit counterintuitive assumption that the allocation must be balanced, so nobody can buy a house that is cheaper than his own house, just at the same price. Okay, and of course you want to maximize the number of satisfied agents, since the problem of finding the deficiency of the market is basically the same as minimizing the number of unsatisfied agents. Okay, and we can reduce this problem to finding a maximum weight cycle cover problem. How do we do this? We construct a directed graph where vertices are agents and arcs are defined as follows. A sends an arc to B if A might choose to buy the house of B, okay, according to the prices and according to his preferences. And there are also important arcs where A not only might choose B's house as his bought house, but it will only also make him satisfied. Okay, there is this difference, and it's not hard to see that every balanced allocation is basically a cycle cover of this graph. So we are looking for so if we assign weights, big weights to important arcs and small weights, for example 0 to other arcs, then we are looking for a maximum weight cycle cover which can be solved in polynomial time. Okay, I just wanted to show you that basically there is a graph problem lying under this problem. Okay, so let's have a look at the other algorithm, which is the case, which is for the case when the alpha is constant. So we are looking for some alpha deficient allocation, where alpha is a small number. So what can we do? We basically do brute force. And we guess the unsatisfied agents, but that's not enough. So we also have to guess those houses that these unsatisfied abled agents will be allocated to. Okay, so we guess these unsatisfied agents, and for each of these agents, we guess the house type that he gets. And we basically just reduce our market by deleting every other chance from these unsatisfied agents' houses preference list. So we delete all the other houses than the one we guessed. Okay, and what we have to do is to look for an economic equilibrium in the remaining market. Okay, so this is just brute force, but so remember that when alpha is 0 and the preferences are not strict, then we cannot solve the problem in polynomial time, or at least it's NP hard. Okay, so this is what I'm not going to talk about, the W hardness result. So we cannot do better than the previous algorithm. Okay, I drew some very nice pictures. I'm very sad I cannot talk about it. Okay. So this is the summary. So we had 2 hardness results and 2 positive results, and the algorithms are, well, I have to admit, they are quite straightforward. So we are still looking for nicer ones in special cases. And I would like to close with some open questions. So first of all, it's not entirely sure that we looked at the right model. So we might look at, or somebody should look at different models as well. For example, where we don't assume that each agent must sell at the price of its house. So for example, an agent might sell its house below the price of its house type. So even if I have the same house as my neighbor has, I mean the same type of house as my neighbor has, and he can sell it for, I don't know, $1,000, I might be satisfied with selling it at a lower price. Okay, so this is one possible investigation theme. And of course, we should look at approximations and kernelizations and the usual thing. And I want to end with a really interesting open problem. I hope you will like this one. So the case when the parameter is alpha, but everybody prefers just one house to his own, it's open. And it's not hard to see that it is equivalent with this graph problem. So we are given a directed graph and some integer alpha, and we ask if we can delete at most alpha arcs from the graphs such that the strange condition holds that each strongly connected component of the remaining graph is Eulerian. Okay, so I don't know the answer about that, and I'm very interested in the complexity of this problem. Okay, thank you. That was all.
Are there any questions?
Have you looked at, did you look at the kernelization for the FPT results at all yet? Or is that just unexplored?
So I thought about a little bit, but I don't really know an answer. I didn't spend enough time on it, but I should. So Toby has a question.
Do people in this area look at structures in the preference relations? In other areas of social choice, there's things like single keepers and preferences, or correlations between my preferences and your preferences.
Well, not really. So they look at this. They looked at this trichotomous model, but no. I'm not really aware of such results. But
even in stable marriages, there's some nice results.
yes, I know. So this area is, I think, quite uncovered yet. So it's quite open to everybody.
Any other questions? Let's thank the speaker. Let's thank Ildi again. Our next talk is by Britta Dorn, who recently finished her PhD at the University of Tübingen and has also got one of those wonderful prizes, a permanent job at the University of Ulm.
Is it loud enough? Okay. Okay, I want to talk about a problem that we worked together with Ildi. And in fact, yeah, it's called the swap bribery problem. Oh, I guess it's so loud, no? Okay. And this is a problem coming from the field of computational social choice. It has several subfields, and one of them are voting systems. And I first want to explain a little bit more about voting systems. So usually when we're dealing with this, we have an election, which is just a pair C and V, where C is the number of candidates and V is the number of votes, is the set of votes. And a vote, you can imagine it as a preference list over the set of all candidates. So these are usually given as complete linear orders. And to make it more clear, I have sort of an example. So imagine like tonight there's the banquet and the restaurant tells us, okay, it's difficult with so many people, so you all have to agree on one single drink for everyone. Like there's only one kind of drink that will be served. We have some choice, but you have to agree upon one drink. So we have some voters, like in our case 4 voters, like for example Saket, Venkatesh, Mike, Fedor, who have to decide. And we have a set of drinks like beer, water, vodka, and lassi. And so the preference list of these voters might look like the following way. The first voter, I don't know who it is, he prefers beer to water to lassi to vodka. And the second voter thinks lassi is the best, so you can see what the preference lists are. And if you're given this situation, this is an election, and we can ask several questions. For example, which drink wins? So this is an interesting question to all of us for tonight. Which drink wins? And in order to answer this question, we need a voting system. I will talk about voting system a bit later. But there are also other questions one might ask. For example, how can we obtain our preferred outcome? And there are several possibilities for that, and most of them are dishonest. One of them is bribery, and this is what I'm going to talk about. Okay, so first I want to explain a little bit more about voting systems, and then I go to the problem of bribery. Okay, there are a lot of different voting systems, and I will concentrate on one special kind, which is called K-approval. And it works in the following way. Every candidate collects points, and the candidate with the most point is the winner. So in each vote, the candidates which are placed on the first K positions, they obtain 1 point each. And the remaining candidates, they will obtain 0 points. And this happens for every vote, and then the points are collected, and the one candidate which has the most points is the winner. So, for example, if this K from K approval is 1, then this voting system is also called plurality. And in this example here, you can see like only the candidates on the first position get 1 point, like beer, lassi, vodka, and water. Each of them gets 1 point. So here it is difficult to determine who should be a winner. But we can also look at K approval for different values of K, like for example, K equals 2. Then we are just assigning points to the candidate sitting on these positions, and you can see that beer will be the winner. And we can also do the same for 3 approval, and in this case it looks different, then lassi will be the winner. So here, if we have m candidates and we talk about m minus 1 approval, then this voting system is also called veto. And you can think of it like every voter assigns one drink that he doesn't like at all, and this drink will get 0 points, and the remaining drinks get 1 point. So if we have a situation like this, just the last position gets 0 points, then it's also called veto. Okay, so this is how our voting system works, and now we're talking about bribery. So bribery can be described as the action of spending some money in order to influence the voters' preferences, and this can happen in several ways. So for example, we pay money to the voters in order to convince them that they have different preferences, or we pay money to the chair so that he secretly changes the preference order. So this is the dishonest way, and this is the way we don't want to to have. But we can also, the same description also fits for campaigning, where you spend a lot of money in order, on advertisement, in order to convince the voters that one candidate is better than another, and this is a positive thing. So if you remember in Neil's talk, she said like it's a depressing situation. We only have NP hardness. We have a lot of NP hardness. So here we're in a good situation, because if you're talking about this year, the bribery where you pay money in a dishonest way, then we are happy to have NP completeness because we want to avoid it. But we can also be happy if we have polynomial time algorithms, because then we just think, okay, that's campaigning, it's cool if we have tractability. So it's a really good situation, everything is interesting. Okay, and how to describe the situation as a computational problem. So the input to the problem is an election. So this is just a set of candidates and a set of votes. We use a certain voting system, which I denote by epsilon. We have a preferred candidate, which is always called P, and a cost function, which tells us how much we have to pay for which kind of change, and a budget, which tells us how much money we can spend in total. Okay, and the question is it possible to bribe the votes in such a way that our preferred candidate wins? And of course, we cannot spend more money than we have. Okay, so we were dealing with a special model of bribery, which is called swap bribery, and it was introduced by Elkin, Falistevsky, and Slinko in 2009. And in this case, the cost function have a special look are special. So every voter can assign a certain price for swapping the positions of two consecutive candidates in his preference list. So I will show it with an example. So we have the voter V. There are three candidates, A, B, and P. And voter V prefers A to B to P. And he also gives us a whole list where he says how much the changes will cost. So if we ask him to swap the positions of A and B, if they are next to each other, it will cost 2. If he has to change A and P and they are next to each other, then it's 3, and so on. And now assume that the briber wants a different vote from this voter, and he wants P to be the first one, then B, and then A. Then he cannot directly ask to swap A and P because they are not consecutive. So he has to ask for a whole set of swaps. So first, he might ask, like, please swap A and B. This will have a cost of 2. Then the vote looks like this, so A and B are swapped. Then he will ask to swap A and P here. Then the vote will look like this. And then he has to ask for B and P, and this will end up with the vote that he wants. And we will have a total cost of 6. Okay, so as a computational problem, we can write it like this. The input is an election. We have a preferred candidate. Then for each voter, we have a cost function, which looks like in the example, somehow like in the example, and a budget. And the question is whether there is a set of swaps which have a total cost less or equal to beta, such that our preferred candidate wins. And so in case you know a bit about computational social choice and these voting problems, and you might know the problem possible winner, it is just a special case of swap bribery if we assume that the costs are all in the set 0 or some positive delta and the budget is 0. So it's just if you know it. Okay. So in the first paper where this swap bribery was invented, Elkin, Falistevsky, and Slinko already gave some complexity results. Here I'm just concentrating on the results for K approval. They made a whole case study for K approval, and they could show if the number of candidates or the number of votes is constant, then for any K the problem is solvable in polynomial time. And as soon as M and N are unbounded, there are 2 easy cases, that is plurality and veto, that we've seen before. And so we know for all other values of K, if they are fixed, the problem is NP complete. This follows from the complexity of the possible winner problem. And it's even NP-complete if the costs are just from the set 0, 1, and 2. And okay, somehow surprising, if K is part of the input, then the problem is already NP-complete if there's just one single voter and you want to convince him to change something. Okay, so this was known, and what we wanted to do is we wanted to analyze the same problem for K approval from a parameterized point of view or from multivariate point of view, where we combine several parameters just to find out how it all works. Okay, so we looked at different things like the complexity depending on the cost function and the budget, then the number of candidates and the number of votes. So these were the most natural parameters. So the first thing was to consider the cost function, and we found that if all costs are uniform, that means like if every swap has the same price, then this problem is solvable in polynomial time. And you can show this if you transform the problem into a network flow problem. And it's interesting because we have some kind of dichotomy here, because as soon as there are two different costs, then the problem is NP-complete, and it's also W1 hard with respect to the budget. And this can be shown by a parameterized reduction from multicolored clique. So this is the complexity depending on the cost function. Then we also looked at the complexity depending on the number of candidates. And here we could show that the problem is FPT with respect to the number of candidates. This can be shown like by transforming the problem into an integer linear program, where the number of candidates the number of variables just depends on the candidates, and then use a Lenstra. And this is quite cool because we can use the same method for other voting systems, not just K approval, but for a whole set of different voting systems. And it's also very cool because the same method applies to a lot of problems coming from voting theory. Like you can show that all these problems are FPT with respect to this parameter as well, like possible winner, manipulation, control, lobbying. So in case just you've heard the names, and these most of them, they are problems where you usually want them to be NP-complete because they are dishonest, like manipulating or controlling or lobbying, and you're happy if they're NP-complete. But now we know if the number of candidates is small, then it's FPT. And this is a setting which happens quite often in reality, that the number of candidates is small. Like if you think of a presidential election, there are not so many candidates. Okay, so this was the second big thing. And the third block was the complexity depending on the number of votes. And here you can remember, here you can remember what I said in the beginning for the results. If K is part of the input, and if it's unbounded, then the problem is NP-complete already if we just have one vote. So if in order to get results here, we should combine the number of votes with some other parameters, like for example with K or with beta. So we will start like thinking about combining N with K. And here you can see that if we just use brute force, then we will get an algorithm with runtime m to the power of O of k times n. And there we asked if it's possible to get the k or the n out of the exponent. And we did several things. So the first case was if we fix k and take n as a parameter. The second one, if we fix n to be 1 and k is the parameter. And then in the last step, we looked at another combination, n and beta. Okay, so we will start with k is fixed and n is a parameter. And we could show that using color coding, this problem is an FPT. So we get this running time, and you can see if k is fixed, then it's FPT with respect to n. So the second situation is that n is equal to 1. So we just have one single vote, and the parameter is k. And we could show that in this case, the problem is W1 hard with respect to the parameter k. This can be shown by a parameterized reduction from clique. Okay, so this is the case that we have the combination of n and k. And the last thing was to look at the combination of n and beta. And here we have this result. If the minimum cost of a swap is 1, then this problem is in FPT with respect to the combined parameter n and beta. And we showed this by kernelization, and this is quite easy to see, so I think I can explain it here. Okay, so how does it work? So this is our election. So here you have to imagine here are all the votes, like all the preference lists, and we know that the candidates sitting on the first K position, they will get 1 point each, and the remaining ones will get 0 points. Okay, and if you look at these votes, it will be like this, that P is probably not the winner of the election, that's why we have to bribe. So it means that probably P is sitting on some 0 positions here, and we have to convince the voters to swap P somehow to get on a 1 position. And also there might be some strong candidates sitting here getting a lot of points, and we might want to swap some of these strong candidates to a 0 position. So we have to do a lot of swaps, and we know that the minimum cost of a swap is 1. So of course, if the budget is small, like this, then you can see that it will be too expensive to swap a candidate from here all the way to a 0 position because we don't have enough budget. So in fact, they are just, not all candidates are relevant, some of them are too expensive anyways, so we don't have to look at this whole thing, but we can cut the votes, so we can just look at the relevant candidates that we are able to swap within the budget range. So we can cut this whole instance so that it looks like this. Okay, then we lose some information. Some candidates that sit here and they got points in this part, we somehow have to keep track of that. And we have to make sure that their votes count. So we add some more votes that take into account this situation. And we can show that this remaining profile is small, as you can see. We can show that it only has this number of candidates and this number of votes. So we get a problem kernel depending on n and beta, so the problem is in FPT with respect to this combined parameter. Okay, so here is again a summary of all the results. So yeah, these are the main 3 things, that the complexity depending on the cost function, on the number of candidates, and on the number of votes. Okay, and since this was just started, there are a lot of open questions or interesting problems, so we've just looked at the most natural parameters, but of course there are other ones that might be interesting. Then we have focused on K approval, but there are so many different voting systems, it might be interesting for the others as well. Then there's also the destructive case of swap bribery, which means there is not one candidate that we prefer, but there is one candidate that we hate and we want to avoid that he's winning. So how do we have to swap so in order that he is not winning? And also one might ask whether this model of swap bribery really reflects reality, or if there's some better model to, how to describe bribery. So there are many interesting open problems. So thank you.
Are there any questions?
The number of candidates I always thought was often not a very interesting parameter because there's only a bounded number of distinct votes, and then you can just use brute force to argue that many problems are polynomial for that reason.
Yeah, if you bound both the number of votes and the number of candidates, then you can always use brute force, but
if you just bound the number of candidates, because there's only a bounded number of different votes, and then you're just interested in the cardinality of those sets.
But you can have so you can have a lot of people voting the same way, or do I get your question right?
Yes, but you just have to know the count on them. So for example, manipulation, the argument first given that manipulation is easy in the bounded candidate case was just that argument I've given.
Okay, so for the swap bribery, they also considered this case, but usually the algorithms were just in XP, but it was not polynomial. Or am I getting it right? So if I understand you right, you say like if the number of candidates is bounded, then we have polynomial time solvability.
Well, for manipulation, there's a simple argument.
Okay.
I'm just wondering why that argument doesn't sort of carry over to swap.
So I don't really know by heart how it worked for manipulation, but I know that for swap bribery it was not known before, so we know.
Does anybody else have a question?
just a technical question. Did you look into membership into W1 for your W1 hardness things?
No.
Okay.
Anyone else? I have a question. In your reduction multicolor clique for your theorem 1, was it an edge representation strategy or a vertex representation?
I think you need, so if the question is, yeah, you need both.
Thank you.
Yeah.
You know, and one more question. It's interesting that if you parameterizing on the number of voters, that it's FPT to do bad things to an election using integer linear programming. And the question is whether you know of the evil Republican operations in the U.S. where there's a lot of money sloshing around and there's not that many candidates. Do they run integer linear programs to optimize their effect on advertising in elections? Do you know if those people use integer linear programming?
I don't know, but so also maybe we should think about like a real algorithm, not just using Landstress result, but a real, so maybe we could sell it.
I mean, they might be.
I don't know, so I have no idea. I'm not politically involved.
Thank you. Any more questions? Let's thank the speaker again. The last speaker of this session is M. Praveen, who will tell us about his prize-winning paper on the parameterized complexity of problems about Petri nets.
Okay. So let me start with an introduction to Petri nets. So let me start with the finite state transition systems, then I will extend it to Petri nets. So finite state transition systems, one of their uses is to model sequential processes. So here is an example. So we can think of it as a directed graph, and let's say we have a token in one of the circles here, and then we can, according to what the sequential process does, we can kind of move around that token, right? So now we want to generalize this to model concurrent processes, where let's say we have two processes, and let's say we want to model synchronization. So imagine a process here and a process there, and somehow we want to make sure that a process can go from here to there exactly when it synchronizes with the other process where it has to go from here to there, right? So this is a natural way to model that, where we say, okay, so let's have, instead of a directed edge, let's have some kind of a hyper edge, where in order to go from here to there, we should have both of the processes, should be waiting at these two respective places, and then they can simultaneously shift to the place, right? So this is a kind of simple motivation for Petri nets, and now we have this kind of generalization. We introduce another generalization where instead of having just one token in each of those circles, so we call these circles as places and this as a transition, right? So instead of having one token in each place, we can have multiple tokens. So we can think of them as number of processes being available in a cluster or whatever we are modeling. So okay, and we can also have weights on those edges, right? So we can say, okay, if this transition has to fire, then it has to take 3 tokens from there, provided they are there, of course, and it has to take 2 tokens from here, and then it will put 2 tokens there and put 3 tokens here, right? Okay. So this is the full generality of the Petri nets that we are going to consider. Okay, so here is a full-fledged example. This is an example from this paper. So this Petri net has 5 places, P1, P2, P3, P4 and P5, and 4 transitions. So this is an initial marking. So marking is just something that will tell you how many tokens are there in every place, right? So initially there are 0 tokens in P1 and 1 token in P2, 1 in P3 and 0 in P3 and P4. Okay, so now we have, this transition is enabled in the sense that all its input places have enough tokens. So basically we don't allow negative number of tokens in any place, right? So keeping that in mind, this transition is enabled because all its input places have enough tokens, so it can fire. So what it will do is take 1 token from each of its input place and put 1 token in each of its output place, right? So it took one token from P2 and put one in P1, and P3 happens to be both an input and output place, so it just took it and then immediately put it back. And accordingly, the marking changes like this. Right, so then we can continue like this. Now this T3 is enabled, so it will take the token and put it into P4, and now T2 is enabled, and then it will take the token from P1, and since this edge is weighted by 2, it will take one token from there and put 2 tokens here. Okay. So now T4 is enabled, so it will put the token back here and then put one token there. Right. Okay, so basically there was one token here, it went around once and became 2 tokens. So this process can go on, and in the next round it doubles again. So basically you can see that this place is kind of recording the number of times the token went around. Right. So every time one round goes on here, the number of tokens can kind of potentially double. So the number of tokens here can be as much as 2 to the power of the number of tokens here. Okay. Okay. Fine. So with this example, now we are ready to define the problem that I'm going to tackle. So the first problem is called coverability. So given a Petri net with some initial marking, the coverability problem asks, so first of all, the coverability problem comes with some marking, some target marking M curve, and the question is, can we reach a marking M such that M of P is greater than or equal to M curve of P for each place? Right. So this is the coverability problem. So for example, in this example, suppose M curve of P had one token in P3 and one token in P4. So that marking is not coverable, because at any time we can have a token either in P3 or in P4, not in both. Right. So that kind of marking is not coverable. And the other problem is called boundedness. Is there a bound on the number of tokens in any place in any reachable marking? And so for example, here in this example we can see that if we keep firing this T3 and T4 repeatedly, the number of tokens in P5 can keep increasing. So given this initial marking, we cannot say that, okay, so there is some number n beyond which the number of tokens cannot increase. Given any number, we can find a reachable marking where the number of tokens is greater than n. Right. So boundedness problem asks whether is there such a number n such that the number of tokens will never go beyond. Okay. So the classical complexity of these problems have been studied. There is an exponential space lower bound, and it holds even for a constant path width. So here by path width I mean path width of the underlying graph. I will come to what is the underlying graph a little bit later. And there is also a matching upper bound. So here almost just means that the lower bound is something like 2 to the root n, and here it is 2 to the n, but the problem as such is exponential space complete. Okay, so these are some of the related works that have been done. So the complexity of this problem has been actually quite well studied. So this is one of the studies where so this is a multi-parameter analysis, in the sense that this upper bound is just in terms of the total input size, which includes the number of places, number of transitions, and the size required to specify the initial marking and so on. So here they did a multi-parameter analysis considering the number of places and the number of transitions differently and so on. And in particular, they proved that the space requirement is exponential in the number of places and logarithmic in the number of transitions and the maximum arc weight. Okay. And they proved the corresponding lower bound also, corresponding parameterized lower bounds. So this is a model checking problem with logic called mu calculus. So just like we have monadic second order logic for specifying graph properties, mu calculus is a logic in which we can specify some kind of properties of Petri nets. And here it is shown that model checking that calculus on Petri nets requires space polynomial in the size of the formula and exponential in the size of the net, again with corresponding lower bounds. Okay, so this is one of the more recent works where they study problems, related problems like reachability on a model called synchronized transition systems. So remember the example of synchronized system that I shown. Here they consider a slightly different way of representing synchronization, but essentially it turns out to be equivalent to one safe Petri net. So one safe Petri net is a Petri net where the number of token can never be more than 1. So they did some parameterized analysis of these kind of models, and okay, so this is one more work that I will be referring to later. So this is work by Flamen-Grohe, which is some kind of a fundamental study of parameterizing many standard classes. So FPT is, you can think of it as a parameterized polynomial time, right? So you have some parameter in which the running time can be arbitrarily large, but on the input size the running time is polynomial time. So that FPT is basically para p time. So here they kind of do some fundamental analysis of what happens when you parameterize other complexity classes, for example polynomial space or and some well behaved complexity classes. Okay, and this is one more work where so there is on digraphs there are problems called pebbling problems, and parameterized complexity has been studied with respect to tree width, and there are some FPT results. These actually relate to something called elementary net systems, which are somewhat similar to the Petri nets we have seen, but not exactly similar. So elementary net systems happen to be finite state systems, but as we have seen, the full general Petri nets can be infinite in general. Okay, so here is what is proven in this particular paper. So let K be the vertex cover number of the graph underlying the Petri net. So what I mean by the underlying graph, so here is the example again. So basically in the underlying graph what I want to say is, basically I want to put an edge between two places if they are interacting with each other somehow, right. So if there is this kind of transition, basically we can see that this place is somehow connected to this place, because if a token from here has to go there, it has to wait till there is a token here also. So there is some kind of an interaction between these two places. So you can here like this you can argue that every place is related to every other place. So basically this is kind of just replacing the hyper edge with the corresponding clique. Right. So do this with every transition and we get the underlying graph of the Petri net, and then let K be the vertex cover number of the underlying graph, and let W be the maximum arc weight. So as I showed, so there can be arc weights on some of these edges. Let's W be the maximum of those numbers, and the result is that coverability and boundedness can be solved in space f of kW comma poly. Right. So this is called para P space by Flamen-Grohe in the paper. So basically this makes sense because the original complexity of these problems is exponential space complete. So we want to see whether these parameters play a role in making those problems hard. Okay. So before moving further, I just want to say a few sentences about the motivation for doing this kind of study. So after all, even if the parameters are very low, we will still require polynomial space. Right. So this is not exactly a study where we would want to finally implement a practically efficient algorithm. Right. So but the motivation here basically was to try and get some insight into let's say a classification of Petri nets, which of them are hard, which of them are easy, compare it comparatively with each other, maybe not with respect to polynomial time, right. So compared to finite state systems like finite state automata, Petri nets is much less known. So automata much more is known, but it much more is known basically because people have asked many questions about finite state automaton and try to answer them, right. So there are a lot of characterization for answer to the complexity theoretic question may not result in a practically efficient implementable algorithm, but at least hopefully we will get some insight into Petri nets. Okay, that was the motivation. Okay, so let me give a brief overview of the technique involved. As far as the underlying graph and the vertex cover is concerned, the technique is very similar to what happens in the usual graph theoretic problems, right. So if you have a vertex cover of size k, the remaining vertex can be classified into 2 to the k groups, right, where so these are, let's say this is the vertex cover and these are the 2 to the k groups, where every vertex, any two vertices here will have the same set of neighbors in the vertex cover, right. So if in a if we take the underlying graph of a Petri net, and if the underlying graph looks something like this, then again we can do some similar classification, right? So instead of so in a normal graph we will have edges which are just binary relations, but in a Petri net we can have in general hyper edges, and in particular weighted hyper edges, because there are arc weights. So this 2 to the k will become no, the 2 to the k will be actually much larger in case of Petri nets, but still it will be function of only k and w. W is the arc weight, right? So if we do a similar kind of classification in Petri nets, what happens is if we take 2 places in one group, and let's say one of the places here has a transition, let's say, which takes 2 tokens from here and does some manipulation on the other places inside the vertex cover, then every other place in the same group will have exactly the same transition. So anything that one place can do in this group can be done by any other place in that same group. Okay, fine. Now, now how do we make use of this fact to come up with better algorithms? So here is something called something that I have called truncation lemma in the paper. This is actually known much before. This has been used before also to come up with complexity theoretic arguments, especially in the context of counter automata. Okay, so here let's see what happens. Let's say we have a Petri net and we have a firing sequence, and let's say we track the number of tokens in one place. Let's say P1. Let's say this is the variation in the number of tokens as we fire the sequence, and let's take another place P2 in the same group in the sense of this classification. Okay, so let P2 be another place in the same group, and let's say this is how the number of tokens varies for the same firing sequence, right? So what truncation lemma says is that if this variation in the number of tokens is suitable, by suitable I mean that it should start at a low value, go to a sufficiently high value, and then come back to the low value, right? So if there is a sufficiently high dome like that, then there is always a way to somehow cut off a large part of the dome and put it on top of this P1 without any of the numbers becoming negative, right? That's very important. Okay. So this is basically a consequence of pigeonhole principle. This is a very elegant proof. I won't go into the details, but what is important here is that if in the beginning, let's say there was an upper bound of C on the number of tokens in both the places, right? Now what happens is that here there will be at most 2C tokens because they just get added up. Here, so I have just shown 0 for simplicity, but it will be a small number here in the worst case. Okay, right. So now we have a classification of the places in terms of the vertex cover, and now we also know that between 2 places of the same group, something like this can be done. Right now we want to put this together to argue that there is a better algorithm. Okay. So how do we put these two together? So for that we have to have a small sneak into Rakov's upper bound, Rakov's exponential space upper bound. Okay, so here it is. Suppose you have a Petri net with 2 places, just a very simple example. Suppose you have a Petri net with 2 places, and suppose there is a firing sequence with at most C tokens in all the intermediate markings. So you begin with a marking and you end with some marking, there are some intermediate markings. Suppose in all those intermediate markings you have at most C tokens. Right? Then claim that we can obtain an equivalent sequence of length at most C plus 1 square. Right? Because if there are at most C tokens, there are at most C plus 1 square distinct possible markings. So if the sequence is longer than that, then by pigeonhole principle there will be some 2 markings which are equal to each other, and then we can just remove the sequence in between these 2. Nothing will happen. Right? So this is actually a very important part of Rakov's argument to get an upper bound. But looking at this and looking at what we have seen in previous slide, we can say something. Right? Suppose if the 2 places that we consider here are in the same group with respect to vertex cover, then truncation lemma gives us a better bound. Right? So because we can basically transfer all those C tokens into this, and what remains is just one place with maximum C tokens. Right? Okay. So what Rakov actually does is to give an upper bound on firing sequence which will cover the target marking, right. So, covering problem basically gives us a target marking M curve and asks us if there is a firing sequence which covers that marking. So, what Rakov does is to say that if such a sequence exists, then there is a sequence of length not very long, and that length, the bound on that length is given by a recurrence relation, right. And using this fact that we have seen, we can basically play around with that recurrence relation and make the recurrence relation grow slower. So, the original recurrence relation has an upper bound of double exponential length. So, a non-deterministic Turing machine can guess such a sequence in exponential space and say whether that answer is yes or no. So, here basically using this fact and playing around with the recurrence relation, we will get. Okay, so I will just conclude. So, basically we have seen that with these two parameters we get a para-P space algorithm for boundedness and coverability problem. And so there is so that we can come up with a fragment of computational tree logic, which is also another kind of logic which is capable of expressing some properties, and this logic can express some kind of extensions to these problems, and it can be model checked in para-P space. Right. So this logic is borrowed from one of our earlier papers with my joint work with my advisor. And so as far as future work, so some of these questions have been asked to me by other people also, some personally and some by anonymous referees. What happens to the time complexity? So this is what happens to the space complexity with respect to the parameters. What about time complexity? And what about parameterized lower bound? So is there something like a W hierarchy for the space complexity? Okay. And the other interesting question that I would like to answer but have not been able to is considering feedback vertex set instead of vertex cover as parameter. Okay.
If I understand it right, this old result that you mentioned an old hardness result for alternate baskets nets.
Yes.
Is this result the reason why you didn't consider like tree widths as the parameter but vertex cover?
Yeah. Yes.
And this result also holds when you have unit weights, so or no weights at all.
Yeah, just even with unit weights it still holds. No, actually no. You will need arc weights. Otherwise the existing reduction is log space, but if you don't allow unit weights, I think the log space reduction will not work. Maybe a polynomial space reduction, but I am not really sure whether the whole reduction works. I will have to look through it and.
Is that giving any interesting parameterized complexity?
No, I have not thought about that. Maybe it might give rise to interesting questions. Yes, that's an interesting direction.
I have one. If this is the same parameterization with K and W, and or KW and bound on the number of tokens in the target configuration for the coverability problem.
Actually, if you take the number of tokens as a constant, then all these problems become P space. Basically, because if you see that if C is the constant and if C to the M is a bound, C to the number of places is a bound on the longest sequence. Yeah, but so if you want, if you want something like f of C times C, okay. I don't really know the answer at this point.